All right, let's jump right in. Today, we're going to talk about something pretty wild: sorting the invisible. We're going to unpack the really clever physics that engineers use to separate microscopic particles that are literally all around us all the time. I mean, think about it. How on earth do you sort particles that you can't even see? It sounds impossible, doesn't it? If you can't pick them up, how can you put them into different piles based on their sizes? Well, it turns out the secret isn't in what you can see, but in how they behave. And look, this isn't just some abstract science problem. This stuff matters. A lot. A particle's size is everything. It determines how deep a piece of pollution gets into your lungs, or whether the medicine from an asthma inhaler actually gets to where it needs to go. That's why sorting them is so critical. So if we want to sort them, we've got to get to know them first. Think of it like this. Every tiny particle has its own physical traits that are kind of like its own unique personality. And it's these traits that we can use to our advantage. Okay, so the first big personality trait we need to talk about is something called relaxation time. It sounds a little complicated, but the idea is actually pretty simple. It's just a measure of how quickly a particle can change its speed to match the air flowing around it. Is it super responsive, or is it kind of slow and sluggish? The best way to wrap your head around this is to think about a car's 0 to 60 time. It's basically the same idea. A tiny, lightweight particle, it's like a motorcycle. It can zip up to the speed of the air around it almost instantly. But a bigger, heavier particle, well, that's like a big ol' semi-truck. It takes a while to get going. And we're not talking about a small difference here. It is huge. Just look at these numbers. As a particle gets bigger, its relaxation time doesn't just crawl up, it explodes. That's because the physics says it's related to the square of the diameter. So even a tiny change in size creates a massive difference in how it behaves. This leads us right into the second key trait, stopping distance. This is all about that sluggishness we mentioned, or what scientists call inertia. If you could give a particle a push, its stopping distance is just how far it can coast before air resistance slams on the brakes. It's a perfect way to measure its, well, stubbornness. And this quote from the source material just nails it, because these particles are so incredibly tiny, air resistance is like hitting a brick wall. You just can't throw them. So how not far are we talking? Let's imagine a particle that's about 100 micrometers wide. That's roughly the width of a human hair. Now, what if you could throw it at, say, 22 miles per hour? It would screech to a halt after traveling just 12.7 centimeters. That's it. Its inertia just gets completely wiped out by air resistance almost instantly. Okay, so now we know that these particles have this built-in stubbornness that depends entirely on their size. The next obvious step is, how can we use that? Well, let's look at how engineers built a really clever obstacle course. This is the real heart of the problem, right? We know big particles are stubborn and small ones are nimble. So how do you build a trap that only the nimble ones can get through? The solution is just beautiful in its simplicity. It's basically a four-step trap. First, you get the air moving really, really fast, carrying all the particles along with it. Then, and here's the clever part, you force that whole stream of air to make a super sharp 90-degree turn. Now, the little agile particles, they just follow the air, no sweat. But the big, stubborn ones? Nope. Their own inertia keeps them going straight ahead. And bam, they slam right into a collection plate. And this amazing little gadget is called an inertial impactor. It's literally an obstacle course designed for particles. Only the lightest, most agile ones can make that turn. The big ones just can't handle it. Okay, so the impactor is awesome. It gives us two piles, the big stuff that crashed and the small stuff that made the turn. But what if two piles isn't enough? What if you need to know exactly what sizes are in there, in multiple groups? Yeah, this is the next level of the challenge, right? How do we go from a simple big versus small sort to something much more precise, with multiple size categories? And the answer is so elegant, you're gonna love it. You just stack the obstacle courses. That's it. It's called a cascade impactor, and it's just a bunch of these stages lined up one after the other. Each stage is a little bit harder than the last, with faster air and a sharper turn, designed to weed out smaller and smaller particles as you go down the line. And here's what you end up with. The first stage snags the real heavyweights, the second stage gets the next size down, and so on, all the way to the end. All you have to do is weigh the stuff collected on each plate, and you can build this incredibly detailed profile of your particle sample. It's amazing how much data you can get from such a simple physical trick. Of course, in the real world, things are never quite that perfect. For instance, some hard solid particles can actually bounce off the plate and end up in the wrong bin. So what's the fix? It's pretty low tech, actually. Engineers just put a thin layer of grease on the plates to make them sticky. It's these little practical tweaks that make the science work.
Okay, obstacle courses are one thing, but there's an even cooler, faster, more modern way to use this whole inertia thing.
That's right. What if, instead of seeing which particles can handle a sharp turn, we just made them all race? And that's exactly what time-of-flight instruments do. Imagine a particle racetrack. You shoot the aerosol through a nozzle, and it accelerates like crazy. The teeny tiny, agile particles, they have no problem keeping up with the airflow. But the bigger, heavier particles, our semi-trucks, they lag behind. So you set up two laser beams like a finish line. By timing how long it takes each particle to get from one beam to the other, you can figure out its exact speed. And it's simple. The slower the particle, the bigger it is. You're sorting them in real time, one by one.
So you see, it doesn't matter if it's an obstacle course or a racetrack. The secret ingredient is the same for both. A particle's inertia, its stubbornness, its refusal to change speed quickly. That's the secret code that lets us sort a world that's completely invisible to the naked eye. It's a really powerful concept when you think about it. This one simple principle, inertia, brings order to a hidden universe. And that really gets you thinking, right? What other invisible forces, what other fundamental principles are out there right now, shaping the world we see in ways we can't even begin to imagine?